So thank you all for being here. Honestly, I want to take this opportunity to go through this topic area that it is a very small sliver of cybersecurity. It sits at an intersection of both, computer science, electrical engineering, mathematics, and if you have questions along the way, just reach out. I'm going to go through some of these slides pretty quickly. There's a lot of pictures and things like that on some of these slides. But if you need me to pause or you want me to go back, just let me know. There's probably more content in here than there is time, which is usually my downfall. But hopefully we'll leave enough time for some good Q&A at the end regardless. So you can see the topic there, hopefully on your screens. Talking about exploiting simplified models of complex systems, really with the ultimate objective of hopefully securing systems as well. So first off, I have to say that none of this work just happens in an ether. So the support of many has enabled us to do a lot of fun and cool work. So a lot of this work has been supported by a lot of different people. And like many of you, things also don't happen by yourself, right? It relies on many others to help do really awesome work. So these are researchers involved with our cybersecurity lab. We also have another lab that's related, a little bit smaller, that deals specifically with blockchain related work, but that's not really going to be the focus of what we talk about today. I'd like to build up some context here, right? We talk about computing a lot, but it's important to understand that, our ecosystem of where our work goes, right? So, what are we developing? Are we developing software solutions, hardware, software solutions? What type of devices is our work going into in the future? You can start thinking that computing will be all around us, that we will have not just the computing that we've traditionally seen, but human integration of components. The near distant future might have personal body networks, computing, that the vitamin you take, right, won't really be a vitamin. Vitamin will actually be a sensor network you deploy within your body to be measuring things and potentially interacting and engaging with you. So we've got this future of distributed systems, both within our society, potentially within ourselves, communicating systems that are close by. So if I have a sensor network inside of me, how do I make sure that it is only communicating with itself and not the person next to me who also has their own personal body sensor network? This is an extreme view of what might happen. And so the question becomes, you have this system. It's made up of, many subsystems and subcomponents. And the question I ask from a cybersecurity perspective, do you want to trust more components or fewer components? Give you a moment to pause and imagine you were presented with this scenario of two buttons and having to choose. And normally when I poll a class, it ends up actually being about 50-50 on which way people, on the distribution of what we should do. Should we trust more things or fewer things? So maybe this helps. I may have missed a slide somewhere. Well, it'll work. So ultimately, when we look at a large system, a large set of entities, the ones that we trust are because we're allowing them to violate some policy or they're acting beyond some other established policies. They are entities that are doing something special. And so if you trust everything in your system, it's actually a really bad thing because everything in your system can somehow violate a policy, can do some action that shouldn't normally be allowed. So from a security standpoint, you actually want your system to have very few required trusted components. You should have to only trust a very few number of things. If you look at this from a social circle perspective, do you trust everyone around you or do you trust a few key entities, right? So the answer is usually you should trust very few people, right? But those you trust greatly. So we, in computing, leverage strong security primitives like cryptographic algorithms, trusted hardware modules, things like that. Because this is the traditional view that we generate some secrets, transport the secret, decode the secret. You can see the traditional problem space and solution spaces there. These are pretty well known, right? So you can take computer security class, cybersecurity class. This is the bulk of the work, basically in terms of how do we secure information, how do we generate the secure information, move it, and then somehow use it, which is great. This is the traditional view of our space, where we are trusting these strong security primitives. And we have ways to measure it. We have ways to evaluate how secure our algorithms are, how secure a communication channel is, theoretically. So the question that I would pose to you is going back to the original question of where does our work exist? Well, our work gets embedded in the real world, in hardware. So what happens when you start embedding these functions into hardware? We have this traditional view where we have some function, have some input and output to a function. But there's another view. Functions don't exist in the ether. They don't just exist on paper and in our systems. They have additional information that is a byproduct of the fact that they are instantiated. Here's a little bit more detailed of a picture. When you have some function operating in the real world, it takes resources to operate that, right? It exists within an environment. So, something that's existing in hardware requires usually some kind of clock, requires for sure some power. It also is impacted by the fact that it is within an environment that has a temperature, that has environmental variables and changes that can influence this function. At the same time, instead of just output from a function, you have other things that are produced, right? In a physical world, you don't get everything, you don't get anything for free, right? So doing some action requires some energy, produces some heat, might produce some sound, depending on the type of thing that you're talking about. When things go wrong, there's other cascading problems that might happen. The amount of time it takes to do an operation is also something that, while we consider during design, is something that could also be leveraged. So without going into a huge amount of detail, from physical implementations, we can actually start extracting information. And we'll talk about how in a moment. But here are some pictures actually of cryptographic algorithms that we measure basically the power consumed and are able to either replicate and extract information about a secret key based off that power, or the individual operations that were done within that algorithm. So let's revisit. What if at every stage we could actually start extracting information? So information is leaked during generation, transportation, and decoding of a secret. It's important to note that what we're talking about here are side channels, and they provide additional information. They don't necessarily break things immediately, but they help us minimize the search space or the computational complexity required. Instead of brute forcing an attack, we can actually start leveraging this additional information to reduce our overall search space of what a secret key or some function might be. So how, right? So what we do is we actually are going to relate some byproduct of our system to a fundamental operation. All right, so a tangible example that's a little blurry here is transistors and what happens when they transition. Really, the important thing to note here is we have 4 different transitions, and an equivalent amount of power consumption. So if I'm able to measure power, I might be able to infer something that has happened with a transitioning bit or set of bits. So if we take that as a starting point, we can actually create some really simple models that deal with power consumed. So without going into all the details, because if you wanted to learn about side channels, this could be an entire lecture. But the idea here is we're going to model within a system. If we are to look at all of the bits that are on, there should be a relationship between the number of bits that are on and the amount of power consumed. So we can actually use something called the Hamming weight of the bits. So it's basically the sum of all bits on should be equivalent roughly to the static power consumed. We can also do the same thing for bits that are switching states. So if we were to be able to look at a system and say, here's the dynamic power consumed, I can now relate that to, I assume that whatever, 10% of my bits just flipped states. That is additional information about my system that you probably didn't assume an external entity would know about. So maybe let's do something a little bit more tangible. Let's use buckets as information holders or transmitters. So the first question is, of the two buckets on top, which takes more energy to hold up? An empty bucket or one that's full? That's essentially our Hamming weight measure. Right? We assume that a bucket that has something in it takes a little bit more energy to hold on to. And then the question below, you've got basically 3 different rows of buckets. Which transition would take the most energy from you to do, right? So you can look at how many buckets have switched states between A and B, right? You can count how many switched. You can do the same thing between A and C and B and C. And you can find out which one of those 3 would take more energy, right? And I could maybe measure that by how much sweat you produce, right? So if I measure how much sweat, can I figure out which of the 3 transitions you did? That's a valid question, right? If I can't observe what you actually did, can I measure some other property that I can't see about you? And that's essentially what we're leveraging here in side channel attacks, especially ones that deal with power. So what is our objective? How do we protect against this? Well, ultimately what ends up happening in reality is we try to disconnect the two, right? We try to disconnect the amount of entropy in the system from the models. So people are going to use models. We can't impact that. What we can do is we can change our systems. And so a lot of my work has been in how do we minimize the amount of mutual information between these two entities, the model and the system itself, knowing that we can't change the model. Again, we can only control the system, not the models that people use. So a little bit on information theory. We have these 2 things, right? We have the system itself, the device you've created, whatever that might be, and you have a model of the system that an attacker is using. There are ways to mitigate and get basically no mutual information between the 2. And what that comes down to, one way or another, is holding something constant, holding the amount of basically, if you can get the system into a state where the model says, hey, there's nothing happening, or the system itself is completely constant. If one or the 2 of those happens, you can essentially eliminate the relationship. So what normally happens is people design clever hardware. Right? They basically create hardware that is dual routed. They create systems in which the number of bits on in the system is constant, which has some inherent problems. One, if you look at these pictures at the bottom, the biggest one is that you're paying a huge penalty in area and in power for no added benefit. Right? So security is definitely a trade-off. And there are solutions to try to make hardware better natively. But it's pretty limiting. How can you as a developer do anything? I'm going to pause for a moment since there's a cuckoo clock. All right. So you could extract some information about where I am, by the way, and what time zone I'm in by the number of cuckoos you heard. That would be a nice side channel. But if we look at the fact that, while we can impact hardware directly, how does that help us as developers, as computer scientists? What happens when we have something that is, within a larger system that we don't want to perhaps influence the entire system and duplicate the area of the entire system? What happens if we are writing something for a reprogrammable piece of hardware or special purpose hardware? What if we are talking about something more general that we can define perhaps by a finite state machine of some kind? What if that finite state machine is how we're controlling a nuclear reactor? There are many, many different versions of why a hardware-only solution is not good enough. So pose this question for you. And since I can't see your facial reactions to this, I won't know when you see it. But if I gave you this really simple finite state machine, which hopefully in a computer organization class you've seen, but basically this is a two-stage or 2-bit 4-stage branch comparator. And the question is, if you only were given the Hamming distance and Hamming weight, could you figure out where you were within the within this finite state machine, right? So if I only told you that the Hamming weight was 2, so Hamming weight is the number of bits on, Hamming distance is the number of bits that have switched or swapped. So if I told you that it was 2, you would know immediately what state you were in, right? If you were given 0, you know immediately where you were at. If I told you that the Hamming weight was 1, you don't have as much information, but you've limited your scope of where you could possibly be within this finite state machine, right? So if you have both the Hamming weight and the Hamming distance and enough views over time, you can actually completely recreate where you are within this finite state machine just by observing those two properties. And because there's a relationship between those and the power consumed, now all you really need to do is observe the power consumed by this system, and you can figure out exactly where you were at any point in time within the system, right? So even if this finite state machine were completely obscured, you could recreate not only the machine, but where you're at just based off of some characteristic that you're able to observe, right? So through quite a bit of long work, we actually come to two really simple equations that allow us to secure finite state machines. And they're pretty trivial in nature. And they say, well, if you have a finite state machine where you can keep the Hamming weight constant, that's good. And then if you have the ability to keep the Hamming distance constant, that's great as well. So basically you need these two properties to keep any finite state machine, any one of these processes, from leaking information. So the encoding is easy to achieve and incredibly hard to optimize. So for those of you that have done anything in encoding, there's an encoding called one-hot encoding that will give everything a constant Hamming weight of 1. Done. We've satisfied that first requirement. It's pretty costly, but for now, let's just say that's good enough. 4-5 years of my life went into working on optimized ways to do this. So we're not going to spend that much time. But unfortunately, encoding is not enough. So take the finite state machine on the left. You have this machine that transitions over and over again to state A. The Hamming distance will always be 0. You have no bit switching in that particular instance. And when you go outbound to another state, you are forcing that there must be some kind of Hamming distance. So the very first thing we realized in doing this work is that the process of continuously trying to optimize things and to do a state space collapsing is a huge issue. So it goes against 30+ years of advice and research that says collapse all states to minimize your overall objective. So on the right, we basically say, look, self loops can be a detriment to our encoding strategy, to our ability to secure systems. So we're going to unwind some loops. So on the right-hand side is an equivalent finite state machine. Basically introduces a new state, leaves all other conditions the same. In this restructuring, this allows us to now be able to have an encoding, even like a one-hot work, right? So if every state in here has its own one-hot encoding, you would have basically Hamming weights of 1 on each state, and the Hamming distance between any two states would be 2, because you have basically 2 bits switching in every single instance. So here's some examples. I mean, there's you can do this for any finite state machine. Doesn't matter what they are, what they're doing. So on the left-hand side, you see a secured version of the branch comparator. It takes 2 extra states and a handful of extra transitions. You can do this with communication protocols, right? So on the right-hand side, there's a communication protocol that goes from 10 states and 22 transitions to 16 states and 38 transitions, right? There's a cost, but you'll note that unlike the hardware solution, it's not a doubling, right? We're not requiring 20 states and 44 transitions, right? So we're able to do some things a little bit better and a little bit, I'll say, in a more optimal way from a software perspective, a high-level perspective. You can see some costs there for a handful of finite state machines. This is just a random sampling of them. You do see that in some cases, for some, in some particular situations, especially for finite state machines that have loops on every single transition, you do end up getting 100% increase in states, right? So if you have a transition, a self loop on every single state, you somehow have to double every single one of those. There has been some work related to this that has actually looked at whether that's a requirement or not, but beyond the scope for today. So I did mention earlier that encoding is easy to do, but hard to optimize. So I actually punted on this. I punted to using a theorem prover and constraint programming to generate secure encodings. So if you're super interested in doing it yourself, you can actually go to this website. Let me see if this works or not. You'll have to let me know. If I pull something new into my screen, can you see that? Is it sharing correctly or not? Or do you still just see my presentation?
Yeah, no, I can see it.
All right, wonderful.
See it now.
Wonderful. So if you go to this website here, what you're going to get is a binder that will launch a Jupyter notebook. Oh, look at that. It's actually working for once. And you can actually look at some code here that does exactly this, basically constraint programming approach to developing encodings. So assuming you have something that's restructured, or if you just want to see what it would take to encode some bits, we have a couple of functions here defined in terms of computing Hamming weight and Hamming distance. But you can define number of states, and you can actually see these are pretty standard optimal encodings, binary encodings. So if you were given 3 states, by the way, without any other knowledge, can you encode them using a binary encoding? Absolutely. And what is the minimum number of bits you need? It's 3, but without any knowledge of that, we've used constraint programming to figure that out. You can go through this notebook and you can see some other techniques that we've used, other constraints we've included in terms of, if you wanted to make sure that the Hamming weight and Hamming distance were the same, that this goes through all of that. But in the interest of time, I'm not going to bore you to death with going through it. Just know that, we have done it, and you can actually look at how we use this theorem prover to do so. So just a little aside for those of you that want to go play with code, go to that website, check it out. It's a Jupyter notebook, so you can modify it, and you won't modify it for anybody else. So have fun if you want to. All right. Really, so if I were to summarize everything I just talked about in the slide, so this is 5 years of work in one slide. Everything that we have done for decades has been about making computing smaller and faster. And In automata theory, we talk about collapsing states to create, basically creating loops ultimately. Unfortunately, there's a relationship between our state transitions, and basically the power they consume with the encoding that we've applied. So there's this relationship here. There's this idea of Hamming weights and Hamming distances between states. And ultimately, what we want to do, if we want some semblance of security, is restructuring and re-encoding finite state machines to limit information leakage. So in a slide, that was 5 years of life. And it allows us to start securing any type of process from leaking additional information. All right, so this is going to be much quicker, and then we're going to have plenty of time for Q&A, but it's related. So we're talking about distributed systems. We're talking about these lightweight hardware devices that we have put code into, right? We've, the whole prior set of slides was all about securing processes within hardware, ultimately. So what happens when we start, so this could apply, by the way, to the medical example I gave earlier of having medical sensors within you. But let's take this example of a drone swarm that was actually tested recently, super small. And I'll have you note at the very bottom in the green box, these are not designed for recovery after missions. So going back to why hardware must be secured in some cases, you are designing this UAV that has some pre-programmed objectives that is in hardware. An attacker is definitely going to be able to access your little mini drone because it's not been designed to be recovered. So I'm going to play this video. Hopefully it works. I'm going to skip ahead a little bit just so you can see the size. Here's this F-18 that is dropping these little drones. You can see I don't know if anybody can see that. They're super tiny. They're just basically dropping out there. And they have some missions they're going to do. I'm going to fast forward a little bit. So they are collectively making decisions. So these are essentially somewhat pre-programmed to do 3 different objectives, but they are doing each objective autonomously in their swarms. So let's see if I can get that last picture here. So the last picture I want you to see is that these drones are encircling this target. I may have gone back a little bit too far, but you'll notice that they are going to randomly create this encircling of this target in the corner. So the question is this vulnerable, right? We have got this really, well, it looks like a complex global system. Can we attack it, right? Is this vulnerable? So we start off and we try to do the same thing. So lower left-hand side, we are able to swarm a target. Great. We can actually do it with many agents. We can do it from 3 agents to 3 million agents. You can see their track and trajectory. So we're able to replicate what we saw in that example that the government is using in their drone swarms. So we can do it in 3-dimensional space as well, just for proof. But so ultimately we have these drones, smart devices, doing this. What if I told you that we can accomplish this with 2 really simple rules? After observation, we realize that these agents are moving with, basically, the first rule is move towards target until you've reached some position away from it within some target window. So simple rule, if you are further than this, basically this area, you move towards the target. If you're too close, move away. That's rule number 1. Rule number 2 is the dispersion rule. Find your nearest neighbor and move away from it at some angle. That's it. So 2 rules, 2 ultra simple rules applied to this system allow us to describe the behavior. So as an attacker, I receive one of these devices and I can basically exfiltrate these rules, right? I can understand how it works, or through observation, I can figure out what's going on. 2 very simple rules. And what you end up with is what you saw in the picture. You basically get this really nice distribution around a stability region, around a target. So it appears pretty resilient to attack. We have our set of drones here, and if I wipe out half of them, you'll see that it self-organizes back into a pretty nice region of stability every single time, right up until you lose enough, right? And so get to a point where it no longer makes sense. So minimum number here is we need 3 drones. It still actually works with 2. The moment we lose 1, it's gonna somewhat break. But pretty resilient to attack unless short of taking out all of the drones. So what if, like I mentioned, somebody is able to take the system and use it against us? If you understand that the agents are following these really 2 simple rules, and I have my adversarial agents come in, they can actually corral all of the agents using a pretty simple technique of leveraging the exact same rules that the agents do. The only additional thing an attacker needs to do is be able to keep track of themselves and actually not care about all the other agents. And they can actually do this corralling pretty effectively. So let's see if I have that as an image in the video. So same picture as before, adversarial agents come in and they basically follow the exact same rule sets as the others, except they only care about themselves. They don't care about the other nodes. So you can see that those 5 red agents there are all distributed across the circle, and they've effectively corralled all the other agents using very simple rule sets. So what we've come up with is you have to build in some amount of disruption within your system. If your rule sets are so fixed that they don't allow for any type of variation, you basically end up in these situations where your rule set is too easy to basically exfiltrate and leverage against you. So what we basically do is we have some metrics, some ability of our agents to leave the system, to go into a point of disorganization intentionally. It comes at a cost. So ultimately, we're actually able to address some of these limitations based off of a really simple rule set at a cost, right? So the biggest takeaway here is nothing comes for free, right? We need to start treating security as something that is in our objective function that will cost something. So we have a couple different examples here. It's a little bit beyond what the point of this talk is, but we've investigated what actually is our best approaches to solving problems with very small rule set systems. And basically the short answer is having some amount of randomness within your system is actually most effective. Okay, so ultimately the point to all of everything that I've been talking about is, we used to say trust but verify. I would say that really we should start minimizing what we trust and create really strong policies and protocols and procedures. Assume the worst. Assume somebody has access to everything, your rule set, your device. This is not a new idea. Claude Shannon basically said, the enemy knows your system. And that's basically a reformulation of Kirchhoff's principle in terms of, you should basically assume that your system is open. And I would add to that your enemy probably knows your system better than you do because they've been studying it in ways that you haven't thought about. And they're looking at everything and they're not looking at it from your lens. So it really doesn't matter how or what you've designed. And that's really hard as computer scientists, as developers, that, what do you mean it doesn't matter what I've designed, right? Well, it's what your system can actually do that matters. When I was at Intel, half of our team was built up of people that their entire job was to break into our systems. So as a security architect, there were half of us using formal methods to secure systems, and the other half were basically looking at every angle of the system to try to find ways that it could be exfiltrated and broken. And they were using the systems in ways that was never designed to be used.